We're doing it live! Welcome to Aggressive Mastery. It's Game Dev Micah. And today we're going to look at a little project I put together about how to improve some demanding blueprints by converting them into C++ using artificial intelligence or learned language models. I'm going to do this, well, it's already done using local LLMs, or actually, I used Claude to build this one. But we'll go ahead and tear the code that I built down and rebuild it using GTP just through a public internet web browser in this call. So what are we looking at here? One of the harder things to do is move stuff in a video game. And the more things you move, the harder it gets. And with blueprints, you have basically like 100 to 1,000 times extra overhead to do anything because you're doing it in a full separate video game. Blueprints itself kind of runs like a separate video game on top of your video game or on top of C++. And so when you're sending things from that blueprint area to C++, there's a transversal cost or a management fee or overhead fee that the more you're doing, the bigger that fee is. And so we're going to look exactly at how you can identify that you're being hit with a bunch of overhead, what it looks like in Unreal Insights, and how a learned language model lets you copy those hard areas by just taking a screenshot of the blueprint code and convert it into either a blueprint function library call from C++, which just speeds everything up. So what you're looking at here is 1,000 spheres that are spawned in the center of the screen and just drift apart. And when they get 10,000 units away from the center, they come back and respawn in the middle. That's it. That's what's going on. Now we do this. Ooh, I got two windows up, of course. With this blueprint here. And I'll quickly walk through it. So let's do that. So on begin play, what we have is a instant static mesh component in this blueprint that is just rendering spheres. We have assigned a static mesh of a sphere here. Oh, how's my head doing? Let's go ahead and get rid of my head. Boop. You have a static mesh of the sphere itself, which is just a sphere, and we have a material on it. We do have collisions on here, and this is something we'll look at in Unreal Insights. For having actually collisions generated every frame is most of the workload of the ISM. If we disable this, you'll see it will get a lot quicker, and we'll look at that in Unreal Insights. And so that's what we have, is a collision body of an ISM with 1,000 instances within it of spheres that are just randomly being expanded. How are we expanding them? I'll show you that. But on begin play, we went ahead and we sized two arrays, a transform array, which is where all of our spheres are, and then a scale array, so we can keep the scale of them too. The reason I do that, you'll see later, is because we're scaling the ISM itself. We're making the ISM a little bit bigger and spinning it, and then we're getting the world values for all these individual spheres and then resetting them to a size because that scaling distorts it. And so that's what this object scale is separate from our transform scales, because our transform scales will actually be calculated. So we have two arrays of a set size of our object count, which we have in here is 1,000. We then generate instances, which just comes up here just right above to another call, where we're just going to loop through, generate a bunch of scales, generate a bunch of locations in those two arrays. So then we get all of our generated 1,000 locations and scales. We come back down here and we're actually going to add it to our ISM using an add instances that populates the ISM with all the needed instances and puts them in their locations. And we're also going to spawn a C++ actor. And this is to show an example later on, but of using a native actor versus a blueprint actor, and that the costs of moving large amounts of data, your transforms and your scales every frame, does have an impact. So it's something to be considered. So we spawn a C++ actor, we go ahead and assign our transforms to it, which you'll see later, we'll refresh. And then we'll actually pass those scales as well. And then we store the variable for that C++ actor. So then at this point, at the begin play, we have our ISM component populated with a bunch of locations, and it's just sitting there static. Every tick, what's going to happen? We come down here. Every tick, we're going to take our delta time and apply it to rotate that ISM component. Doing so is where we get all of our motion that we're seeing here. So all this motion's coming from applying that rotation to the ISM component. And how do we get the expansion? Is by applying scale, We just add a little bit of scale to our ISM, and that's going to pull the ISM apart and pull all the instances apart from each other. And that's what's going on. That's what's happening here. But the nice part about that, which you'll see, is that we're not calculating every single instance and how it's moving. No calculation at all. That's happening with the ISM moving, and then we're going to actually grab those spots and save them. And so right here we have a flip-flop. This flip-flop's here because I have the C++ already done, but we're just doing it via blueprints. And so the main workload that we have is right here. We're going to pass in our transform array, how many objects there are, the instance static mesh, and the object scale to a blueprint function. So here I just took this function, gave it a call, and that way we can very well compartmentalize the workload. It's coming in here, and for a full loop, it's going through every single instance and checking, grabbing the transform of that instance now that we modified and we expanded the ISM and spun it. Now the transform is something somewhere else calculated in the world. We go ahead and grab that information. We're going to check and see if we've left our bounds. So we have a passed in respawn distance, 10,000. If we're over 10,000 in ASB or absolute, then we're going to go ahead and reset ourselves to a new random location. We're going to grab our scale, which was passed in through the scales here at that index, and go ahead and assign it. So here you're getting each element in that transform array is getting its location set, its rotation set, and also its scale set. If it's out of bounds, it's being teleported back, and there's a new one as well. So that's the workload. The workload here is scraping the ISM for every single instance, and then finding out if that's out of bounds or not, and respawning. Once we do that, we come back to the ISM and we reset it back to the same location, no rotation, and 1.0 scale. This zeroes out all the movement that was done. And then the last thing we're going to do here at the end of the tick is apply all of our scraped transforms that we did here back onto the recentered and re-nulled out ISM. And that's how we capture our movement without constantly letting the ISM move in different directions. So the ISM is just going to scale a little bit, rotate a little bit each frame. We grab how that impacted every single instance, save it, reset the ISM, and then reapply it. And so here's the reapply call. I have a flip here because we have it in C++ or blueprints. We're doing just blueprints. So we're going to come in here, and we're just going to take a batch update. We're grabbing the ISM, we're grabbing those saved scraped locations and rescales, and reapplying it to the ISM. And so that's the end work. Now I have these two split out because basically this batch update instances is a C++ call, or well, it is. And what we have in blueprints is access to that C++ call. So what we end up saying here is that I'm using that C++ actor to say, well, how about if we ran this one call in C++, would it be faster? And we're going to go ahead and look at Unreal Insights and see that's not faster. So basically, and this is the end result, is when you're going through a loop, when you're doing a lot of frequency, you're going to see that's what you want to convert to C++. When you do just one call, and that call is heavy, like this apply here, it's doing a bunch of physics calculation or collision calculations, that can't really be improved, cannot be improved by moving to C++, because it's just one action, one amount of work that has to be done anyway. But there is some cost to moving transforms around. So if or data around. If your data exists in blueprints, it's going to cost something to transfer it into C++. If it's in C++, it's going to cost something to transfer it up to blueprints if you want to try and work on it in one of those two other situations. So the more you can put the data directly into C++ and keep it there, the faster it's going to be too. But you can pass references, pointers to blueprint-made variables in C++. So you don't have to make more garbage collection, store that data, and deal with the transfer rate. Obviously, I've spent a lot of time in these areas, and I'm already way in the weeds on it. So let's just go on here and look at the Unreal insights of this thing in action. And actually, yeah, we'll do it right now. Everything's blueprint right now. We're using 100 or 1,000 pieces. We'll hit down here in trace. We'll start a trace. Trace started down here. This is firing up Unreal Insights server. It's now going to go ahead and record for us what's going on in the environment and give us a visual display of that. And I've recorded a few seconds. We'll go ahead and stop the recording there, hit the trace window, look at the recent traces, and open the most recent one. Boom. And so what we have here is our visual representation of what's going on. If I click on one of these little bars, zoom in, fill up the screen, you're going to see all the work that happens here. Here's our blueprint actor, and below it we have these set transforms. This is rotating and scaling our ISM. Then we have our scrape ISM here, all these little lines. This is where we're going through and looking at every single instance, seeing if it's out of bounds, respawning it, and grabbing that data. And then on the opposite side, here's where we nullify or recenter our ISM and get rid of the rotations that was applied. And then at the very end here is where we actually do our batch instance update and update the ISM with those scraped values. So one of the big things you want to see here is that these big pink blocks where we're touching the ISM, we can't improve that. We cannot improve that by moving to C++. And we'll go ahead and toggle it on and show it here in a second. But this scrape and rescale, we have a whole bunch of lines, thousands, maybe 3,000, 4,000, 5,000 nodes that are used here. As you use the mouse button to scroll in on those, what you'll start to see as we expand out each one of these calls, so it's like get instance transform, convert to a double, break the transform, get the absolute max, find out if it's over that range, generate new random integers to make that location, make vector. The big thing here is between each one of these calls, you're getting some gray space. That gray space is the transversal cost of going from blueprints into C++ and doing the work and coming back. So the main thing to see here is that the gray space is what can be improved when you go to C++, because in C++ the gray space is much smaller or non-existent, almost incomparable to this, like 100x. And what we're going to do here is you're going to see that from 3 milliseconds, it's going to go to like 0.3 milliseconds or 0.03 milliseconds. It gets super small because of that gray space being removed. We do all the same calls. We do all the same work. We just don't have to travel from C++ up to blueprints and back down to C++. And the frequency of that exchange from C++ to blueprints is all the cost in this heavy workload here. Whereas in updating the ISMs, if we scroll all the way down between these actions, you can see there's some gray space. There's gray space between update overlaps and update the ISM with the adding new bounds to it. But because these calls happen so less frequently, aka they're happening 4 times in total, 1, 2, 3, 4, there's 4 little itty bitty black spaces or gaps in there, where since we're doing this 5,000 times, there's 5,000 little gaps in there. And the gaps are what we're trying to get rid of. All right, so that said, let's go turn on the C++ scrape here and see this reduce. I'll pause the simulation, come back into the script here, turn my flip-flops on. So this flip-flop here means every other frame that's called is going to use the blueprint scrape or the C++ scrape. So we'll be able to look at insights and see the difference right there. Also, we're going to come down here for our update call. So when we actually apply those values to the ISM, and we're going to follow that as well. We have one that happens in blueprints, in C++, and one that happens in blueprints. Same call. With this one, we're going to see these don't get any faster between frames, but we will see that these do increase. So we'll save it, hit play again, boom. You see they start off in the center, and just as they're getting farther out, they're being recycled back. Let's go ahead and do another trace here. I full screen it like this when I'm doing my traces because you're going to get some user interface or the widgets that is the Unreal Engine editor itself costing you something. When you full screen it, you get rid of some of that, and we don't need to look at it, so I just get rid of it. All right, stop our trace. We'll go open up the last one here. And now we'll zoom in. What you see when you're starting to zoom in here, look at that, there's a difference. We zoom in some more. All right. Now here's 2 frames. Let's see, I'll keep the busy one on that side. So on my left side, we have scrape ISM and rescale with the BP header. And then over here on my right side, we have the CPP scrape ISM and rescale. And so you can see from 3.1 milliseconds in blueprints to 98 picoseconds. You know, it's less. It's about so what, 300% less in Sky. So we're going from 8.3 milliseconds to 5 milliseconds, and it's all from doing it in blueprints with all these little gray bars in here versus moving it over and condensing it all down to one call where there's no transversal between every single one of those 5,000 nodes. And that's your huge red flag, or your big win, big easy win on converting things that have a lot of iteration. You know, yeah, all these little lines, which are really just all these gaps between the work, versus cutting that all out and boom. Now, yes, we're covering why convert from Blueprint to C++, but the key part here is that, yeah, as you're learning this or as you're looking at the stuff, you look at your entire code base, the only real thing we need to convert was this call. The rest of it is being called once. It's not looping. So wherever you have a loop, so let's see here, where we have a for loop, that's where you're going to want to convert to C++ performance. All right. Now, how do we do the conversion? That's what this is supposed to be about. So let's pause. One more thing. We're going to do another trace here. So our instance static mesh, that component is highly efficient. The reason that it's taking so much time to update is because we have collisions enabled. So let's just go ahead and show that, because it's a nice thing to know. We're going to go ahead and turn off all collisions and saying collisions enabled, no collisions on the ISM component. Go ahead and save that, and we're going to play again. And now we're going to go ahead and go down here, do another trace, full screen it. Now we're at 120 frames per second, but we're still going to go look at that. There we go. Stop our trace. Ooh, oh, I did two of them. We'll go hit that one. All right. We'll zoom on in here. And now, look at this. Here's 2 frames right here. 5.5 milliseconds and 11 milliseconds. Here's our BP scrape ISM. It's still, both sides, we have our ISM update here, but we turned off our collisions, and so now it's super fast because it's not updating any collision information. We still have our blueprint in ISM's rescale. That's still eating a ton of gaps. But if we look at the next frame where we go ahead and use C++, look at this thing. We're down below 1 millisecond now. We do our roll rotation on the ISM, we scrape it in C++, and then we do another roll rotation and apply it. And actually, it looks like this is the BP apply. So yeah, the workload here between blueprints and C++, we've completely eliminated any of the work here, right? Now what can we do? We're dealing with 1,000 instances, right? Well, let's up the ante here to 100,000. Now, 100,000 in blueprints is going to have an issue if we use the blueprints. So let's just go ahead and turn off blueprints for the scraping. We can still do our flip-flop here for updating the ISM, but we'll just only use our C++ call. Boom. So now we're at 30 frames per second, but with 100,000 components being updated. So you just sort of see and actually, let's go ahead and do a trace on this. With 100,000 instances going through like that, all being done in C++. I'll stop that. I can hear my fan spinning up on the PC here. It's more work for sure. We're doing 100,000 times more work, or well, 100 times more work. I don't really like once it's running all right here. And there we are. So now we have our scrape is being done at 9.6 milliseconds in C++. So if you were to do 1,000 times or 100 times that, it'd be like 90 milliseconds. Well, I mean, you'd probably be up over. I mean, I don't want to do it. We'll lock up the system. But without collisions on the ISMs, and we're doing our applies and doing our scrapes, we're getting 30 milliseconds on that large workload, where it's just not going to happen in blueprints because of the gaps. All right. So the next part would just be, let's convert that call. Let's actually do the big part here. So let's stop this. Come over here. What we want to do is convert this. So what I do is I come in here, I click on my function, get my exposed variables, expand all those out because they'll start off closed like this. Expand them out so you can see the sub, and I'm basically going to copy and paste this as an image over to a LLM to convert it. Get all on the screen here. Now there's a lot of ways to do it. This is how we're going to start. Boom. I do a snipe. And you want to include the least amount possible, just not add extra data for the LLM to think about. And I normally do this in 4K. You can make these images as big as you want, so we'll see how this works because it's going to try and just match it together for you. But anyway, here we go. We got our copy. And I said I was going to use it, so GTP. This is a completely free GTP account. If I hit paste, oh, it won't let me do images. That's right, that's right, that's right. Well, that's a problem, because it will let you do images. What was it that was going on? You might have to load in. Oh man. Okay. What I actually do is I use a local LLM. I use Olama, or not Olama. I use Llama CPP and Gemini 4 as a chat agent. I guess we can still just do it that way. All right. So let's go find our. Boom. Oh, yeah. The screen resolution's busting my. I'm here. One of these will let me move the dang thing. Or not. Okay. Come here. Come here. Windows is such an amazing operating system. I know it's like, what else is better, but whatever. I mean, oh, cool, I don't even have my video on. You can't see me holding my hands on my face. All right. Well, let's just go look at it first. So what this got converted to, heck, we'll just do it here. We're not even going to talk about the native stuff. This was what was generated by the LLM from providing the image that we got. It's a, I told it I wanted to have it provide me a blueprint function library done in C++ with a call of CPP, scrape ISM, and rescale. And then with that image, I said, I defined out, hey, make this. And then when there's errors, I said, fix it. Now let's just do that, of course. And I don't want to freaking lose this forever, but, well, yeah, this part of the presentation is a little bit more doing it live. Chat here, I do have a copilot. I just want to do it for free, but yeah, I'll do it like this. Boom. So there, I pasted in an image using Control V from our screen grab here. I'm going to tell it to create a new, actually let's get a new chat. Paste, please convert this blueprint function call into a new call in our I'm just going to LLM converted. This is just the name of my function library that I have made already, converted, which is just what the files are called. called to CPP scrape live LLM. This call should take in man, oh man. Oh, hey Solar. How long ago you post that part? What up? What up? Just trying something new. I'm recording this, so it's in 1080p, and so yeah, I'm having some issues with dealing with, like, I feel like I'm looking through a microscope. So yeah, we have our call, and it should take in the values from the detail panel on the right of the image, and yeah, only, you know, Opus 4.6, I guess. It's so slow to generate originally. But, I mean, I'm using Qwen 3.5 or Gemini in Visual Studio typically. Because I don't like paying for things or having my data out somewhere else. So I'm using, actually, let's see here. Find out where the freaking Claude code. I think Kylo is what I have to use now. Yeah, for the new stuff. And Gemini 4 AB. So this is what I'm normally doing. You can just paste images in here, and it will do all the stuff. So I like that. But Claude should be just as good, or better, right? So, but I was doing. Ah. Yeah, the nice part about this, what I really think is cool, is that you can just, as we'll see here, hopefully, is take this image and you can just dump it into the window, tell it what to do, it will spit it back out. And I've been doing it in Ask, but then I would do agent afterwards. Ask will just generate the code for you, and then the agent, you can have it apply it or what have you. You know that. But we did make a working cargo grid. You could move cubes close to it, and then check what is the nearest hatching point. Yeah, I mean the problem right now I run into with AI in doing this, and what I'm going to try to define here, is that wherever you let it start to think for you, it gets a chance to be wrong. Where if you can define things like this diagram and the blueprint, you get it working, and then just say, hey, just convert this language of blueprints into the language of C++, it can hit that pretty much one-to-one, and pretty much knock that straight out of the park. The next phase of saying, okay, now it's in C++, now the LLM can just directly see it and understand it, then ask it, hey, how can we improve the performance here? That should hit, and it does. Especially you can copy, like if I go back to Unreal Insights, which is super cool, and say take this call, or rather my entire call here, select them. Down here I can take the callees or the callers, expand all of these out, and get all the different timings down here and values, and do a copy to clipboard. Then you can come back over in the LLM and say, here is my Unreal Insights of this call, and put the call name in there, what have you. What is the most expensive, or how can we restructure this logic to perform better, perform better. and you just paste in the values. Now, it's not stacked ranked exactly, and so I don't, but I've had some decent response out of AI. And I was say, oh, you're doing these calls a whole bunch. We could turn off collisions on it, stuff like that. But it's just throwing words at the screen. You got to kind of know what you need out of it and how to structure stuff around. So let's see how it goes here. Image, and this call should take in, so I'm going to go ahead and try and convert that image again. Please convert this blueprint function call into a new call in our BQ function library called 2CP scrape live LM. This should take in values from the detail panel on the right via reference from the image and return transform and updated transform via that reference being modified. Let's say that. So I am in agent mode, so it might actually shove it in there. I don't like being in agent mode because it can actually do stuff. I find sometimes AI will start to change your capitalizations of your variables because it thinks it's more correct in calls you're not working on. So I like to try to tell it to do one thing. Luckily, we only have one call here, so hopefully it won't screw with it. And so this is kind of like there's this delay where it's now loading up the data on the LLM, doing some interference, and we're just going to maybe sit here for 2 minutes while this is doing it. Oy. That's why I like the local stuff. It seems to be quicker, which is freaking horrible to think about. So in short, you're optimizing? Yeah. In this video, mainly optimizing, because moving from blueprints to C++, that's an optimization thing only. Some calls are not exposed, so you have some issues there where you might need to go to C++ to do the call, but then you could ultimately make it a blueprint call. But really, the question is, what can you, a lot of people are afraid of AI or generative AI, and I'm trying to use it in a way they shouldn't be afraid of, which is as a language converter, blueprints to C++, where I'm saying, hey, if you need to know exactly what's going to happen, and then let it convert it to C++ and make sure that exact same thing happens again. Cool, so it did some work here. And we're going to go in there and just see if we can use the other call and just have it do this exact same thing. So let's see. Now, since we generated a new call here, we're going to have to rebuild the project so that those are exposed. So I'll hit save everything. I think I got to hit tab to make sure it's keep it. Keep it. Boom, boom, boom. Need that. Stop my simulation. All right, cool. Saving all that. Close this out. Let's just head back to it. Where is it? Go generate project files. This is going to scrape all of your .ccc and .h files, find calls, register them, then we go back into Visual Studio here and rebuild the project so that the calls are exposed all the way out into blueprints. Clean. I mean, like, I didn't want to go and show examples in the Giantess Playground because what I'm converting there is much larger, even on the small side, than what we're doing here. So it's like trying to just make it so we can hopefully see most of the code on the screen at the same time and understand what's going on. Is why I just basically built a new little sample. And I am going to put this up as a GitHub link so you can just download the whole project and go poke at it yourself. And what I do want to do is I was talking to Ari, and I have an option to give this presentation for Unreal Livestream. And so this is really that first dry run on it, getting some of the details out there, getting OBS working, and chopping it around, trying to figure out what I'm going to use for video editing, since Microsoft Clipchamp or whatever now requires you to upload everything to them. So DaVinci Resolve and all those stuff. So yeah, all this non-games dev stuff. All right, so Let's do a rebuild. And now we're building the C++ that was generated so we can hopefully find our new call. Oh. So we got a CPP scrape live LLM is what it's going to be. I'm going to hope that this is doing, hopefully we won't get any errors with the build. Cool, build successful. Go ahead and launch the game. Yeah. You know, what you'll run into is that it may not include the needed libraries for the code it generates because it just forgets that part. And so you'll get some errors like, hey, I don't know about what an instant static mesh is. And, well, let's ask AI, why doesn't it know? And it's be like, oh, we probably need to include a library. And so it should all work out. All right, so now we come back all the way in here. Let's see here. We got CPP. There we go. 2 CPP scrape live LLM. So there's the call the LLM just made for us. Well, let's just go ahead and change the pin out. And reattach these things. Now I'll set my respawn distance. Boom. Alright, this would be cool. Head back in and hit play. Hey, what do you know, it works. Love that. It works at 100,000 too. So we just took our our blueprint that we have, took a picture of it, and asked the LLM to just make it. The more you can define there, such as specifically the variables that are coming in, that they're by reference, that what you're going to do is, you know, to make sure that whatever you're doing within that function is able to get data back out, the less it's going to try and guess. And when I say guess, when you don't tell an LLM or AI what to do, right now, you could say on your most optimistic that they'll be 70 to 80% right when they guess. So that means they're going to have like a 30 to 20% wrong. And that 30 to 20% wrong, when you're working on something like this, you might catch it and fix it, no problem. But as you work on it over time, bigger and bigger projects, it's going to continue to inject 20 to 30% wrong guesses. And so, you know, the more control you have over it, the less you let it guess, the better it's going to just be able to make hard code that fits. So, cool. So I think that, I'm just super happy that all worked out. And that we got this running like it is. And we'll go ahead and do another, I mean, we don't really need to do another trace, but we'll do another trace. Stop it, go look at it with our new call. Zoom in. And there you go, CPP scrape live LLM. And you can see there it is, at the 100,000 level. So that's pretty much what I wanted to cover today. It was showing an intense workload and how we lightened it up. The intense workload being scraping 100,000 instances every frame, getting their location, checking if they're out of bounds, and resetting that, which is this here, at the iteration rate of 100,000, has a whole bunch of gaps between each one of these nodes that are called. When you put it in the C++, those gaps get infinitesimal or completely go away, which then means you're able to get performance, where this would just die in blueprints at 100,000. Solar, it's so great to see you, buddy. Thanks for being my longtime friend, and of course, it's cool to see you chatting in there stream. Thank you for coming by. It's made my morning. Hope this was fun hanging out and sort of. Oh, I can turn my face on you for a second here. Camera. Show me. Hello. But yeah, I'm gonna go ahead and recut this probably offline. But it was nice to come in here and actually share some live stream with you. Oh, I'll add you as a moderator. Boom. Try that. Cool. And I'll be at Unreal Fest. If anyone catches us at the end here, if you're going to be at Unreal Fest, it's my favorite place. It's been my third time going. So yeah, my little vacation. So hopefully we can chat about this a little more there or what have you. But have a great day. Good to talk to you. Ciao.